we all grew up knowing that there were regenerative receivers, and we got, maybe we got one for Christmas, one of these $3 radio kits, and you build it, and well, maybe you heard a station, and you hear the strong shortwave broadcast stations, but all in all, they weren't very impressive. But what we find out is that from the invention of the regenerative receiver in about 1912, for almost 20 years, regens were the best radios in the world. And like if you look at amateur radio, they went from talking 10, 15 miles to talking to Australia using regenerative receivers. So this presentation is going to take a look at regens and help you come to understand how that was possible. And then afterward, we'll take kind of an extended break. And there are 4 working regenerative receivers up here, so feel free to come up and poke around them, sit down, listen to them, get a feel for them. Okay, first slide, please. Part of the circuit we're talking about here goes all the way back to Marconi and his crystal sets. Here in his patent in April 1900, you'll see this transformer kind of thing in here. And if we go to the next slide, we'll take a closer look at that in the receiver. And what it is the classic 2-circuit tuner. These coils are coupled magnetically. You've got one circuit out here that's a variable cap and a coil, and then the rest of the circuit is the antenna, which looks like a capacitor to ground, a little bit of resistance in the signal source. On the other side of that transformer, you have another tuned circuit, another variable cap, another coil, and this allows you to couple the energy from the antenna down to the radio efficiently and select the station you want to listen to. In this case, it's just a crystal detector, a headset. Next slide, please. What happens using more than one tuned circuit, that first tuned circuit, second tuned circuit? A single tuned circuit might have a response curve that looks something like that, but if you cascade multiple circuits, that shape of that response curve comes down like this, and that gets you more rejection of other signals here. So having more than one tuned circuit's a pretty good deal, and so a lot of the better early radios were set up this way. Next slide, please. The other thing in that circuit is how the 2 coils are coupled. If they're coupled not so tightly, you don't get a whole lot of response out of it, but the selectivity, the narrowness, can be pretty narrow. Probably what you want to do is couple at the so-called critical point where you get maximum signal through the thing, and things still aren't too wide. If you couple too tightly, then this kind of double hump curve happens here, and things get wide on you, and you sort of don't want that. So you end up with 3 controls, one to tune the primary, one to tune the secondary, and a third control to adjust the coupling between the 2 circuits. Next slide, please. So, long about 1906, 1907, Lee DeForest invents the triode, and this circuit out here is that same double-tuned crystal set type thing, except instead of a diode here, instead of a crystal here, we now have this triode amplifier, and the detection takes place in the grid circuit, which looks kind of like a diode. Electrons can only flow one way in here. But the important thing about the triode vacuum tube is that now we can apply power locally to make the signal louder. In the crystal set, all of the energy that got to your ear came from the transmitter, and maybe the transmitter is 1,000 miles away, so it gets pretty weak. So now we have the opportunity to amplify signals and make them louder. DeForest invented this circuit. The tubes that were in use were pretty crude. In many commercial applications, they decided not to use them just because of the expense and the hassle of operating them. These things work better than crystal sets, but only maybe just a little bit. So, next slide, please. The man who solved this problem in 1912 was Edwin Howard Armstrong, and this is one of his patent drawings. And of course, this is a patent drawing, so you're not supposed to be able to understand it. But let's try just a little bit. Out here, we have a double-tuned transformer, and this coil here is actually part of it, to a variable capacitor here. So this is sort of DeForest basic Autodyne detector circuit, except we find over here there's another tuned circuit. And what Armstrong did, he had been a radio experimenter for quite a number of years, and he was an electrical engineering student at Columbia in New York. And so he's experimenting, trying to improve the Autodyne detector, and he gets a suspicion that here in the plate circuit of the Autodyne, he gets a suspicion that there are RF radio frequency signals in this circuit. Now, DeForest, who really didn't understand his own invention, categorically denied this. But Armstrong, being an old RF guy for a number of years, he wasn't old, he was about 22, he decides, let's put a tuned circuit in here. We can use that tuned circuit to peak the RF signal that's there and maybe make the signal stronger. And so he tries this, and his results right here. Great amplification obtained at once. And what he did, next, I think we have here's a picture of his apparatus. I won't spend time on this evening, but there's a lot of New Jersey tie-ins here because ultimately he takes this experimental setup. Here's the Autodyne tube on top of it. Here's some tuned circuits and stuff. He took this stuff in 1914 down to Belmar, down where Info Age is going to be, along with David Sarnoff, who built this place, demoed the radio for Sarnoff. It was the best radio on the face of the earth at the time, and the rest is kind of history. Might suggest you read Empire of the Air if you haven't yet. Go to your local library, get a copy, take a look. Next slide, please. Okay, so what he did, he put that extra tune circuit in there, and that causes energy to be fed from the output of the amplifier back into the input of the amplifier. In a simpler to understand circuit, here it is here. Let's just take, remember we have this input circuit going on over here, and an output circuit here through the headphones. Let's take some of that energy that's going to the headphones and feed it back into this transformer here. Now, there's a lot of misunderstanding about what's happening there. A lot of old books say it amplifies it over and over and over again and makes it louder. That's not quite true. But what it does is you have this tuned circuit out here, and all circuits have loss in them. There's resistive loss in the copper, the wires, and there's magnetic losses and all kinds of things going on there, keeping you from having a perfect circuit. But now if we take some energy and feed it back in here, we make up for the losses in the circuit. And when we do, with the quality of the circuit, the lack of loss in the circuit is called Q. And by feeding this energy back, we improve the Q of the circuit. The voltage right here that the grid of the tube sees goes up with increasing Q, and also the selectivity goes up. So it's a win-win deal. You get better selectivity, you get better amplification. And if you increase the amount of feedback here, the third thing that happens is this thing becomes an RF signal generator. It oscillates, it makes RF. So all of this was real important because in one invention here, Armstrong makes a superior radio in terms of selectivity and sensitivity. He makes an oscillating radio that's able to detect continuous wave Morse code signals, which people knew would be a good deal, but they didn't have any effective waveguide receivers. He takes care of that. And oh yeah, because it's an oscillator, you've got a transmitter as well. So the guy was really influential there, and his connections at Columbia enabled him to document this. If you go to the old publications and things, they did oscillograms of the thing oscillating and all this kind of stuff. So it was really a significant piece of work. Armstrong's one of my heroes. So later on, down here on the end of the table, we have a basic Autodyne detector circuit with an extra tuned circuit out here on the end, and sure enough, it's a regen. You can sit down here and listen to the broadcast band, get a feeling for how that works. Next slide, please. So let's talk a little bit more about the modes of operation of a regenerative receiver. And the first is regenerative, not yet oscillating by itself, and we get improved sensitivity and improved selectivity because of the Q multiplication that takes place because we're feeding that extra energy back into the input of the radio. The problem, this is the mode in which you use these receivers to receive AM signals. One of the problems with these are that you have what's called square law response. And what square law says is that if the input signal increases, say doubles, the output signal will increase by a factor of the square 4 times, or if it triples, you get 9 times. Sounds like a good deal, right? However, when the signal drops off by a factor of 2, or rather a factor of, yeah, it goes the other way, and the signal drops right down into the noise very quickly. And in that case, no amount of amplification after the detector will get you your signal back. So straight regenerative receivers aren't really all that good for broadcast use, but it's because of the square law response. However, when you use these receivers to receive Morse code in the oscillating mode, and the word used is Autodyne. It's a heterodyne receiver. You have a local oscillator that's mixing with the incoming signal, generating a heterodyne down in the audio range where you can hear it. And because it's oscillating by itself, it is an Autodyne receiver. And that's the term that was used by the communication receiver people through all of this time. They'll talk about Autodyne receivers. They'll talk about TRF Autodyne receivers with tuned radio frequency amplifiers in front of them. And an Autodyne detector has a linear response, so it can be very sensitive by virtue of putting an audio amplifier on the output of it. You can hear very weak Morse code signals with these things, so they can be very effective radio receivers for CW operation. Next slide. Here's a radio that was designed in 1914 by the U.S. Navy at the Washington Navy Yard, Bureau of Steam Engineering. That's what SE stands for. There were also 2 guys involved in this named Israel, and is it Pierce or Price? Do you remember, Marv? Pierce. Anyway, they formed a company and sold the same radio under the name IP501. And this was the first Navy radio that had the vacuum tube built into the same box. All the earlier sets had essentially a crystal set and then a detector box outside of it. This was sort of a landmark in 1918. And this, I guess, let's go to the next slide here. The circuit of this thing, this is really a simplified version of the radio you just saw, which has all sorts of tap switches and things to cover a wide frequency range. But out here, you have that double-tuned input circuit. You have a tickler feedback, regenerative detector, and then outside of that box, you have 2 stages of audio amplification. So this regen set with 2 stages of audio was a pretty standard radio from 1918 onward. At the dawn of the broadcast era, this was the kind of radios that were hanging around and the kind of radios that came into use. As broadcasting grew, they gave up on regenerative receivers pretty quickly. And a lot of people think it was because of patent considerations, but I think it's because they didn't work all that well. And the TRFs, the 3 dialers, worked a whole lot better than the regenerative sets. But this was the basic circuit there. But this circuit continues in commercial telegraph use and in amateur radio use because it works pretty well for those purposes. The only thing that isn't good about this circuit is you've got an adjustment here, a coupling adjustment between the 2 of them, and a feedback adjustment over here. And when you try to tune to a different frequency, you find yourself not having enough hands to adjust all of this stuff at once. So this is where amateur radio was in about 1921. And a guy named John Reinhardt's, who wrote QST. Next slide, please. 1921, he published the first of a series of articles, and he says, our radios need to operate at higher frequencies than the broadcast sets. Amateurs have been banished to the short waves above 1500 kilohertz, below 200 meters. And that old circuit didn't work so well up there, and Reinhardt's leaned on it a little bit, took a look at what other people were doing, and he comes up with a simplified radio. It's just got a tap on the input. There's only one tune circuit here. It's got tickler feedback coming around this way. It's simple and easy to build. In fact, the first article, his coil is just sort of a handful of wire with some taps on it. But Reinhardt shows people how to build ham radios that they can build at home and get working without a whole lot of trouble. And thousands of these were built. Next slide, please. Here's a picture of a homebrew Reinhardt's receiver. This is part of the John Dilks collection. When you see these things, you'll usually find they have the 3 tap switches. In here's the flat coil that I talked about, and many of them have some extra binding posts on the front. This one doesn't. They had 3 extra binding posts to put another coil on there so you go to even higher frequencies with it. So that's the Reinhardt's receiver, and it got a lot of people on the air, is what it did. So as about 1921, 1922, as we proceed through the 20s, there are elaborations to regenerative receivers. And as new vacuum tubes become available, which is being driven by the broadcast industry, then improvements get made in the ham and commercial communication receivers as well. In the early days, with the early triodes, it was hard to get any real RF gain out of those tubes. You could put an RF amplifier in front of your Reinhardt's receiver, and yeah, maybe it helped a little bit, but it wasn't a really good deal. But as time goes on, we get first tetrodes, screen grid tubes, which make pretty good RF amplifiers, and then pentodes, which make really good RF amplifiers, and remote cutoff pentodes, which let you have effective RF amplifiers with controllable gain so that you can keep the whole thing working right. So we see a steady progress in regenerative receivers through the 20s into the early 30s. Next slide, please. And so one of the landmark articles here in regenerative receiver history happens in QST in January 1933. George Grammer, who I don't know if he was technical editor at that time, but he ended up being technical editor. And George says, let's take a look at all these radios that everybody's built, and let's figure out what's right and wrong with them, and let's build a really good one. And he called this article Rationalizing the Autodyne. And what he came up with was, in some circles you see this 1V1 configuration. That means you have one RF amp, a detector, and one AF amp. It's a tuned RF stage. You don't necessarily need to tune your RF stage. Sometimes it's good just to have that stage in there so that the antenna waving around in the wind doesn't detune the detector. But if you build an effective RF amp that's tuned in both places, it improves selectivity and sensitivity. It's a little hard to do. You have to be careful doing it. But so he designs tuned RF amp using the newly introduced remote cutoff pentodes to get a fair amount of gain out of it. You need to have effective shielding so that your RF amp doesn't turn into an oscillator on you. He did some work on band spread tuning. If you just have one big variable cap and you want to tune slowly to carefully tune CW signals, that's difficult. So he has a scheme for band spreading. He points out the requirement for stable power supplies. You try to run one of these radios on an AC supply, and in a regen you're operating it just slightly oscillating, and now if the AC supply changes, the frequency changes, it stops oscillating. It's real ugly. A lot of amateurs ran their radios on batteries for that reason. And the other thing that happened was pretty early on, they realized that electronically regulated power supplies would be helpful. And in fact, Over here, and you'll get a chance to take a look at it and play with it later on, is a receiver that was built in the 1930s, was inspired by Grammer's article. And when I got the thing and looked at it for a while, I said, yeah, that's what this is. Read his article. 1934 handbook showed a hard regulated power supply, which I built here on the box on the corner. It's got a triode series regulator and another pentode and a little neon bulb to be a voltage reference. So it's a real regulated power supply. And they were doing that in 1940 to keep their Autodynes under control. All of these circuits, this receiver in general is pretty much turns out to be an elaboration of the national radio SW3, which is this ugly little black box here. We have one of those here running tonight. Those were introduced in about 1931, a couple of years before Grammer wrote his article. So this is real interesting reading if you're trying to understand these radios. The other interesting thing here, this was in 1933, very beginning of 1933, and just the year before, QST also published an article about using a crystal filter in the IF amplifier of super heterodyne receivers. And up until that point, especially down in the lower amateur frequencies, like 160 meters or 80 meters, a good TRF Autodyne worked better than almost any superhet you showed up with. It was more selective, was more manageable, and all that kind of stuff. But here, a year before, they published this crystal filter article, which now makes the superhet a good deal for communication receivers. And so this 1933 is kind of starts to be the end of regenerative receivers for amateurs and commercial operators, and this is where superhets start coming into the market. And that's kind of important for a couple of reasons. One of which is that up until this point, a reasonably talented amateur could build a good receiver, could build a good TRF Autodyne in the basement. You get to superhets, it gets a whole lot more complicated. You just spend more money on parts, and it's a lot harder to get them going. So it really kind of marks the beginning of appliance operators in amateur radio. And by the end of the 1930s, everybody's using a factory-built superhet, and these radios start dying out. Next slide, please. This is Grammer's schematic. He's got a tuned RF stage out here using a 58 remote cutoff pentode. There's a RF gain control pot down here. That's important because regenerative receivers are real easy to overload if you have too much signal. So this gives you an effective way to have gain when you want it and turn it down when you don't. The detector here is a 58. Gain regeneration is by varying the screen voltage, and they've got the typical national big choke for a plate load, which pentodes need a high impedance plate load, and this circuit allows this detector to deliver a lot of audio output. So all you need is one triode to drive a headset. When you play with these radios, don't clamp the headset on your ears, put it up in front of your ears, because if you get a crack or a pop, it's going to be real loud. So you need to be a little careful. So that was Grammer's rationalized Autodyne. In fact, when I found this radio, it was at a spring meet up at the AWA, and I looked at it. It had all these coils, and it was built kind of nice. That's a Radiola 16 cabinet. When you look at it, the guy did a really nice job, and I said, this is an interesting radio. So I bought the thing, and I took it home. I was living over in Pennsylvania. I took it to a guy named Jerry Mathis, who was kind of the grand old man of ham radio in the neighborhood. Took it up to Jerry's. I said, hey, Jerry, tell me about this radio. He opens the lid. He says, rationalized Autodyne. Closes the lid. Well, he told me a little bit about it that I had already figured out, but I didn't know about rationalized Autodyne. And that's when later on I found Grammer's article and came to understand this. So a lot of these radios got built in various shapes and forms using information from Grammer's article, and I'm real glad to have it. These radios work real well. You can understand how people use them to talk to the far ends of the Earth. They're selective. They're stable. They're stable enough to receive sideband on 20 meters, for instance. And they're on the lower frequencies. They're reasonably selective. You get up on 20 meters, well, it's pretty marginal. But down on 160 or 80, you could be pretty happy using a radio like this. They work a whole lot better than a cheap superhet, like say a helicopter's S-38 or something like that. These work remarkably well compared to that. 1933, however, wasn't the end of the TRF Autodyne. Here's a picture of the inside of this set down here. You'll see that there's separate shielded containers around the RF amp and the detector. That's important because if you try to share this wall between the two, you get coupling, the thing takes off and oscillates and all of that. So that was one of Grammer's contributions, was to point out the necessity for that. You'll find out that guys like National were already doing that. You take a look inside the SW3 here. Next slide, please. But 1933 wasn't the end of all of this. The commercial and military end of the world was still using TRF Autodynes. This is what I consider to be the high water mark for the shortwave regenerative receiver. This is a radio system that was called RAL that the Navy designed in the early 1930s. And these were used extensively all through World War II on smaller ships like destroyers and submarines. And even after the war, some of these survived for quite some time. The RAK is a low-frequency set. It tunes from something like 16 kilohertz up to 600 kilohertz, and then the RAK tunes from something like 300 kilohertz all the way up to 22 megahertz. So it's a true HF receiver. Next slide, please. This may be a little hard to see, but I'll give you a quick tour of the schematic here. There are two tuned RF stages and a detector, and they are gang tuned, single knob, and some trimmers to keep everything lined up. So you kind of understand that from the rationalized Autodyne we looked at. Over here, there are two audio amplifiers, so there's plenty of gain coming out of this thing. And right in here, there are not one but two audio frequency filters, which improve the selectivity by keeping you from listening to all that other stuff that gets by the detector. So they've got a low-pass filter here that rolls everything off above 1200 hertz, because these things were intended primarily for Morse code use for CW. And then there's a peaked audio filter that can be used in parallel with that to get you a peak at some convenient frequency, like say 700 or 800 hertz, so you can really dig down in the noise and hear Morse code. Again, there's good, effective RF gain control because these are remote cutoff pentodes. And another embellishment on this radio is that there's a tube out here that is a variable audio limiter, and that keeps you from getting your ears blown out when a strong signal comes along or you get a lightning crash. So these were quite sophisticated radios. They work surprisingly well. I wouldn't bring one down here tonight because it's about 100 pounds altogether with the power supply and everything. But that was the RAL. That was, like I said, I think is the high watermark for the TRF Autodyne. There were other regenerative receivers being used in World War II. The Germans and the Japanese used them almost exclusively for field radios. Their super heterodyne technology and vacuum tube technology had not quite caught up to where RCA was. And so over here in the end of the table is a radio called the Torn EB, which was a German backpack set. You'll want to heft the handle and figure out if you really think it's a backpack set. But that's a TRF Autodyne. It's band switched. It has two RF stages. Uses these funky metal shielded German tubes, which is a whole story in itself. So these four radios are all working. I'd like to invite you to come up, sit down, play with them. We'll help you out with them if you're having trouble figuring them out, and take this opportunity to hear some of these radios play. Thank you for your polite attention. Are there questions?
Yeah, I got one.
Yes.
Who built that radio for the Navy?
RCA.
RCA built it?
Yeah. Yeah.
Weren't they concerned about oscillation when they were using these, let's say, on Navy ships, that they might put out a signal?
The reality of that is that the signal has to make its way backward through these two amplifiers. And so the amount of signal that gets out to the antenna is real limited. Now, that IP501 I showed you, which is just a detector hooked directly to the antenna, and in fact through that double tune circuit to make sure that there's good coupling to the antenna, you can, I had mine running, you could literally hear it a mile away.
Yeah.
Okay, there was a real problem there, but these radios were shielded and laid out and designed such that there was no problem.
Good.
Other questions? Yes.
Did they survive shock and vibration pretty well?
Guys like the RAL did. They were specifically designed to work just fine when the cannons were fired. And of course, you have other vibrations on the ship from the engines and stuff. Yeah, they are seriously constructed with all that in mind. Other questions? Oh, Walt?
Just one more thing. The tickler, that has DC going through it, right?
Yeah.
But the tune circuit is AC, right?
Yeah.
How is it that the DC that's going through the tickler circuit actually induces your...
Well, it's a DC path through the tickler, but there's RF in that circuit as well. And it's the RF that's getting inductively coupled back into the tune circuit. But yeah, the DC supply for the tube is coming through that
circuit. There's AC riding along on that DC circuit?
Right, exactly.
Okay.
And yes?
The gentleman was asking about vibration. When I was a radio man, I had one of our radio stations was under a 5-inch 54 cannon.
Okay.
And believe me, we had a little vibration there.
How much would the radios move in frequency?
Well, when I first got aboard ship, I didn't know we were under this cannon. So I'm just sitting there, I said, oh, let me relax a little. And that cannon went off. I swear to God, I went out to see about maybe 6 inches. And all this dust coming down. So they took a beating, believe me.
Were they shock mounted? Or?
No, they had rubber
Forward mounts.
Yeah, pants under. But they really took a beating.
Yeah.
We had a transmitter. This is a little off key, but our transmitter, it was Northampton. It was the most powerful communication ship in the Navy. We used to shock the bosuns. I'd take a fluorescent light, walk by the transmitter, and it would light up.
Do they have like clamps to hold on the tubes? So
yeah, they take all those steps, and they're pretty successful at it. I had a friend who was in the Coast Guard in the Vietnam era, and you may know the Collins R390 receiver, which is a very heavy, very military thing. And even that receiver, he said when they were at sea for about a month, then he'd go in and realign the receiver because everything was getting vibrated out of kilter, and he could tell that it was worth realigning it.
That was before they put the R390, Collins R390 oscillator in there.
Oh, okay. Well, he apparently thought that the IFs moved and everything, so he took care of it. Okay, thank you for your polite attention. We're going to kind of take an extended break, come up and play with the radios, get something to eat. And then we'll do that.
Hey Steve, how you doing? Good. I hated watching all those TVs pop through there. Why? It's like, no! Brainwashing the boys too, it's like imprinting you.
Your mother was frightened by subscribed to it. Now, I was just about ready to shut the thing down because there had been no traffic on there.
I'm not getting any digest, but I'm just getting individual emails.
Right. Well, there's no. I don't know if there's a digest capability there. I didn't see anything lately. I have to check because I had to change an email.
You fit a little back into the coil. And
I thought I was supposed to.
got it.
You know what I did with the I made a full oscillator with one.
On all
a transmitter, a little